Hajun, would you like to do the short introduction before Manu
Yeah, sure.
start?
Okay, shall we start?
Sure.
Okay. Let's start the last keynote session. So let me introduce the speaker, Manu Sridharan. Manu is a professor at the University of California, Riverside, and he previously worked at Uber and developed a static analysis system there. And before that, he worked at IBM Research and Sun Research. And today, he'll talk about his recent work about using pluggable type systems. So Manu, would you please begin?
Thanks so much. So thanks everyone for watching. Today, I'm going to be talking about some of my recent research on moving fast with high reliability using pluggable types. And this has been done with a bunch of collaborators, my students, Manli Ran and Nargis Shadab at UC Riverside, Lazaro Clapp at Uber, Subarno Banerjee from University of Michigan, Martin Kellogg and Michael Ernst from University of Washington, and Martin Schaaf from Amazon. So let's start with some background. What are pluggable types? This is a technique that's actually been around in various forms for quite some time. The idea with pluggable types is that you can extend your compiler with additional type checking for new kinds of properties beyond the kind of compilers that come built into the language like Java. And we're going to be focused in this talk on the Java language. And the way that you can add type annotations is via, in Java, the Java annotation system, though that's not fundamental, you could do it via comments as well if you wanted to. So in terms of pluggable types from Java, one of the main original papers on the technique was published actually in 2008 in ISTA, and it's been embodied in the checker framework since that time. So let's take a look at an example of how pluggable types work. And we'll do it with kind of the classic or maybe most common use case for pluggable types in Java, which is trying to prevent null pointer exceptions. So here's a simple code example. We have a logging routine that just prints out the two-string representation of an object. And in this other method, foo, we're calling this logging routine with null, which is a buggy way to do things. So with a pluggable type system for nullability, the typical assumption is that if you don't write an annotation on a field or a formal parameter, the tool assumes that parameter to be non-null. So here, the programmer didn't write anything. We'll assume that this parameter should never be null, and immediately we'll report an error because that parameter shouldn't be null, and we see at this call site that we're trying to pass in null. So let's say that we want to allow passing null to this routine. What you can do is add a type annotation. Here it's written nullable on the parameter. So this is telling the tool that you are allowed to pass null to this function. But now you'll get another error because the tool observes that we're dereferencing this variable x that's been marked as nullable. So this can lead to a null pointer exception. So we can get rid of this error by adding a null check in the log routine. So here, if x is null, then we just return. And now the tool will be able to verify that this code is free of null pointer exceptions. So this kind of technique has been embodied in the checker framework since at least 2008. So we're doing new research in this area. So what's new right now? So my research has been broadly focused on finding bugs for many years. And before recently, I was using different kinds of approaches to attack this problem, primarily whole program static analysis and dynamic analysis. And I thought it would be interesting to kind of go through some of the trade-offs between these techniques for bug finding to see where pluggable types can play a nice role. So if we look at whole program static analysis, and let's just go left to right here. So we don't need annotations, right? Oh, sorry. We don't need annotations. You can just analyze code as is and try to find bugs in it. And that's a big advantage. Say, if you're trying to analyze code from other companies or code on the internet, we can cover all the paths. So in you can potentially build a verifier that catches all bugs of a certain class. On the downsides, you do get false positives, potentially a significant number, depending on how your technique works and whether you're trying to verify a property or just find bugs. But I think the bigger issues, honestly, in practice are error messages. So sometimes errors can be good, but if you talk about complex whole program properties, very often it's extremely difficult to explain the error to the programmer. There was a great discussion of this in the CACM 2010 paper from the Coverity folks about how they had to turn off various error checks just because the messages were not understandable. And also, overhead of this kind of analysis can be quite high. So there have been various techniques recently to try to do incremental and modular analysis rather than trying to do things at a whole program level. But getting results, complete new results after a change, can still take on the order of minutes to hours for large programs. So now let's look at dynamic analysis. And the key advantage of dynamic analysis is that you don't get false positives because we've executed the program and we've observed the bug actually occurring. But there are downsides to dynamic analysis. So you're not covering all the paths. Fundamentally, you're going to have this issue that you might miss bugs because you didn't have the right inputs to expose them to your analysis. And then in terms of error messages, they're often clearer than static analysis because you have a concrete execution path that witnesses the bug. But if it's a whole program property tying together many different source files, I would argue it still can be hard to understand what's going on in some of these issues. And overhead can also still be high, depending on what kind of analysis you're doing. And dynamic analysis can often suffer from difficulty in deployment. If you're trying to test a system kind of in a production configuration, you're going to have to find a way to get your instrumented code or your monitor running in that system. And often in practice, this can be challenging. So where do pluggable types fit in? Well, on many axes, I would argue that they have advantages over these other approaches. So in terms of error messages, I think that pluggable types can give you clearer error messages than either static or dynamic analysis. The user does have to understand what the type system is doing, but once they do, the key advantage here is that the errors often only relate to code in a very local scope, say within a single procedure. Now this assumes you're not doing things like whole program inference, which we don't really do in the techniques in this talk. If you did do whole program inference, then you start running into the same issues that you do with whole program static analysis. The other thing is that, again, if you're doing limited global inference, your overhead can be quite low. This requires some proper engineering of your tool, but the overhead should be on the order of the same cost it just takes to compile the code, which is much, much lower than a whole program static analysis. And also in some ways, lower than dynamic analysis in that once you're running your code, you're not adding any overhead. So the key downside, I would say, or question about pluggable types is right here. because we're trying to avoid doing whole program analysis, developers need to add some annotations in order to get these systems to work. So I think that's the key question here, is that will developers actually write these annotations that are needed to make these systems work? And for a long time, I think the assumption in our community was that this is actually quite impractical, that developers just want to ship features, and if you ask them to do any extra work to achieve a higher level of safety, they're just going to ignore you or blow you off. But I think things have changed recently, and one of the key driving factors in this change are deployment models for mobile applications and what happens when you have a crashing bug in a widely used mobile app. And obviously my experience is from Uber, where I was working. So the issue with bugs in mobile apps is that it can take quite a long time to deploy a fix if you have some critical bug and you need to get your fix out to users. So if you have a good deployment system on your backend servers, you can potentially deploy a bug fix once you've written it on the order of minutes to hours. You just need to update the software on the server, and then your users are using that new version of the software without any change on their device. In contrast, when you have a bad crashing bug in a mobile app, it can potentially take days to even weeks for all your users to end up on the new version of your app that fixes that bug. This is because of issues like getting approval in app stores and then waiting for a user to explicitly do an update. They might not need to be on a good internet connection to download the new version of your app. So this is kind of out of your control, and this can take a while. So a key lesson that I learned when working at Uber on these kind of apps is that if you have a bad enough cause of crashing bugs, developers will work with you to annotate their code to avoid crashes. So we had a lot of success and at Uber with these kinds of techniques. And another advantage here that developers really like is that if you can get your pluggable type system running inside the compiler with low overhead, they enable what's called a green master, where basically if you check out the latest version of the code and you run your checker on that code, it should report 0 warnings. And we did actually get to that point for more than one type-based checker at Uber. So you can run these things on every build. They run fast because they're modular and incremental very naturally. And in my experience, achieving this level of checking with pure static analysis is very difficult. Either you just can't block the build on these errors, so developers are free to commit their code even if the static analysis is reporting issues, or the static analysis is so costly that you can't even run it on every build, so you need to run it maybe overnight. So there's a lot of potential for pluggable types to yield greater software quality when deployed, but there are some key challenges that need to be overcome. So you need to have a low false positive rate for sure. So if most of the errors being reported by your tool are false positives, again, developers are just going to ignore you. You also need to have a low annotation burden. And this is a trade-off, right? You can't take it to 0. Developers are going to have to write some annotations, but it has to be low enough that, given the significance of the bugs that you're catching or eliminating, developers decide that this is worth it. And finally, you need to have low enough build time overhead. So if your tool is still taking, minutes to hours to run, then it's not going to be deployable in this kind of green master scenario that we would like. So in the remainder of this talk, I'm going to present 3 different projects, recent projects in this area of pluggable type systems that we've been working on. I'll first talk about NullAway, which is the work that we did at Uber on practical type-based null safety. Then I'll talk a bit about some more recent work on verifying complex object initialization patterns. And finally, I'll talk about some work that's still in progress on using similar pluggable type system techniques to prevent resource leaks in Java programs. So let me start by talking about NullAway. So when we started this work at Uber, the motivation was exactly what I mentioned before, app crashes. Uber really needed null safety for its Android apps. Null pointer exceptions were causing a significant percentage of crashes in Uber's Android apps. And as I mentioned, there are existing tools for doing this kind of type-based checking. So the first tool that was tried at Uber was a tool called Eradicate, which is actually part of the Facebook Infer system. And it worked well in terms of they invested a lot of effort, and actually using that tool got the null pointer exception rate way down. So it caught a lot of bugs. But there were some downsides. So this tool was still too slow. It couldn't run on every single compile, partly because it ran kind of outside the compiler, and also it ran on a separate intermediate representation than what the compiler was using. So they were able to only deploy it on continuous integration, and this led to a bad developer experience. Developers were annoyed that they had to wait on this tool and fix all its bugs before they could commit their code. Also, it caught many bugs, but it still missed a few. So we also tried the checker framework, and there were still issues with the build time overhead being too high. And also, we found that there were too many false positives. And here, what I mean was that in some sense, the annotation burden was too high. You had to add a lot of annotations, but those weren't actually catching more real bugs in our experience. So the goals that we had when we decided to build NullAway was to try to make it fast, try to catch most bugs. Note that I don't say all bugs. We were willing to compromise in some areas in order to make the tool usable. And we wanted to have a very low false positive rate. So one of the main techniques that we used to achieve these goals was making various trade-offs in terms of how sound we wanted the tool to be. So a nice way to phrase what our high-level goal was we wanted to have no false positives in practice for checked code. And let me talk a little bit more about what I mean there. So our strategy was to introduce some unsound assumptions in places where we saw that the false positives were too high or the annotation burden was too high. We said, let's try being unsound for this construct. But then, as we deployed the tool, we could look at crash data from the field, from our deployed apps, see what was actually causing null pointer crashes, and then tweak these assumptions to try to eliminate as many of these crashes as possible while still keeping the tool usable. So where we ended up with was a few interesting techniques. We had a novel algorithm for checking initialization, which is unsound, but quite practical in that it seemed to eliminate, at least in the Uber code base, all the initialization bugs that we saw. And we had unsound handling of certain other features. I'll give an example on the next slide. The other key thing that we did was in our handling of third-party libraries, we found that the only way to do this reasonably is to handle them optimistically. This means that basically we assume that if you had a third-party library and it wasn't annotated, that it was not going to be the root cause of null pointer bugs. So this doesn't sound great, but we found that the alternatives were worse. So if you try to do a pessimistic handling of these third-party libraries, assuming basically that they can wreak havoc whenever you pass in a null value, and that they might always return back a null value to you. That just has an impractical annotation burden. We couldn't get that to work in practice. There is a downside here, which is that this is still probably the main cause of bugs, null pointer bugs that are missed by our tool. And we have some ongoing work on trying to do better for these kinds of libraries with a bit of inference. So let me give you an example of one of our unsound assumptions. And this is around method purity. So let's say we have this class foo holder with a field foo that is nullable. And let's assume also that we have standard and getter and setter methods for this field. So now let's look at this code. We get some foo holder object, and we check if the foo field is not null. And if it's not null, we're going to call this set foo method with null. So that's going to set the field to null. And finally, we dereference the field, which causes a null pointer exception. Okay, so this is buggy code, but our tool is not going to emit a warning here. And the reason is that we assume that this set foo method is pure. So we unsoundly assume that it's not going to have side effects and it'll act deterministically. So clearly this is unsound for examples like these, but we found that in practice, this kind of code occurs very rarely. It was just not at all a cause of the real world null pointer exceptions that we were seeing in the field for our apps. So in terms of low overhead, there wasn't really any magic here. All we did was sort of engineer the fastest type-based null pointer checker that we could. So we built it directly as a plugin to the Java compiler. We based this on ErrorProne, which is a great bug finding framework for Java that was written by Google. We did leverage the library from the checker framework for data flow analysis, but we didn't use any other general type checking framework. We built everything from scratch, and we use standard techniques to speed things up. So we tried to be lazy. The data flow analysis is the most expensive part of this tool. So we tried to only run it when absolutely required. And we were very aggressive about caching results so that we didn't do this expensive work more than was necessary. So let me talk about some of our results. So in terms of overhead, this was a big win. On average, we only saw about a 15% overhead over just compiling your code. So that's pretty low and much lower than these alternate tools. And it's low enough that you can run this on every single build. And that's what Uber still does for all their Android code. Anytime you compile it, NullAway is running. So then there's a question of how are we affected by these unsound assumptions? And what we did was we looked at 30 days of crash data across all of Uber's Android apps and looked at all the null pointer exceptions and tried to figure out what was the root cause here? Why did NullAway not catch this? And what we found was that we had achieved our goal. In terms of the code that NullAway was fully checking, so excluding third-party libraries, none of our unsound assumptions actually led to any null pointer exceptions. So the remaining causes of the actual exceptions were optimistic handling of libraries or bad suppressions. So NullAway has a way for a developer to just suppress a warning and say, please just ignore this. And sometimes those suppressions were wrong and leading to crashes. And finally, there was some complex reflective code that NullAway did not handle. So we did another study where we looked at 18 open source benchmarks and we compared the additional issues that were discovered and reported by the checker framework as compared to what was reported by NullAway. And in this study, for all the additional issues, we studied them, and they did require some more annotations to type checks, but there were no true bugs that were root caused to those issues. So that just gives another piece of evidence that the unsound assumptions that we made in NullAway are reasonable. So that's all I wanted to say about NullAway. You can go read our FSE 2019 paper to get more details, or I encourage you to just try it out. It's available on GitHub. It's pretty popular, both in open source and in industry, and it's still very much supported. So try it out and let us know how it works for you. Okay, so next, I'm going to be talking about more recent work on verified object construction. So in this work, we're using a pluggable type system to verify some complex object construction patterns that we see a lot in modern code. So where do these patterns come from? Well, the issue they're trying to deal with is that in Java, objects that you build often have a mix of properties that are required and some that are optional. So here's a simple example. We have a user identity class. It has 3 fields, name, ID, and nickname. And both the name and ID field are required, but the nickname field is optional. You can either provide it or not provide it. So how do we typically construct objects in Java? Well, we use constructors. So here, you could provide 2 different constructors depending on whether or not the client wants to provide a nickname. And let's say that we have these constructors and some client tries to build an invalid user identity object, see, just providing a name, but not an ID. Well, as you know, the compiler is going to reject this. You'll get a compile error because there's no constructor signature that matches just passing a single string argument in. So constructors are the standard ways to build objects. And the pro here is that the compiler will do some verification that the arguments are sensible and will reject your code if you pass in the wrong types or the wrong number of arguments. But there's a bunch of negatives. First, as you saw, we had to define 2 different constructors in that case. And you have to write each of these by hand. And as the number of optional properties grows in your class, the number of constructors you have to write for all the different combinations will start growing exponentially. So that's definitely a problem. Also, can argue that when you're doing constructor calls, the arguments are positional. So in this previous case, we saw that we had a string name and a string nickname. And if you look at a call to the constructor, you just see 2 strings being passed, but there's nothing in that code to tell you which one is the name and which one is the nickname. And as you add more and more arguments, it gets harder and harder to read the constructor and know what arguments are getting passed for what purpose. So this has been an issue in OO code for quite a while. And there's like a well-known design pattern that helps you build more readable code in these scenarios. It's called the builder pattern. So here's our same user identity class written with a builder. So now we have an inner class user identity builder, and we have different routines to gradually build up the state of our user identity. So we have a method to set the name, we have a method to set the ID, we have a method to set the nickname, and when you're all done, you can call this build routine, and that will return your final user identity object. And very often, this code is written with each method returning the builder itself. And so you can write your construction code in this nice fluent style, right? So here, I create a builder, and then I invoke name and ID to set the name and ID, and finally I call build to get my final user identity object. So this looks much nicer. As you can see, it's very clear what purpose each parameter is getting passed for. So this is flexible, easy to read. We avoid this issue with having to write an exponential number of constructors. And in fact, there are various code generation frameworks like Project Lombok or AutoValue that, given a Java class, will automatically generate all this builder code for you. So that's really nice, but we have a downside here. So now let's think about our erroneous pattern again, where we wrote this code, but we only passed a name. So unlike the constructor case, this code compiles just fine. So then the question becomes, what's going to happen at runtime when you write this code? I think the best case is you get an immediate runtime error telling you you're constructing an invalid object. So at least you know something bad happened, but still we're a lot worse off than the static analysis case, where we were detecting all of these issues right in the compiler. Even worse, sometimes you don't get an immediate error, you just end up with a malformed object. And we saw that this can even lead in some scenarios to security vulnerabilities when you don't invoke the right methods to construct your objects in a secure fashion. So this is a big problem. Although we have flexible and easy to read code, we don't have any kind of guarantee that the required arguments are actually provided. And this is something that developers hit all the time. You can see all these issues on the Project Lombok GitHub related to this. And in fact, the lead said that, we get this feature request every other week, and the feature request being detecting missing required property calls at compile time. And that's exactly what we do in our approach. So we've built a system that gives you static safety for uses of the builder pattern. And in fact, it's quite a bit more general than that, which I'll talk about in a few slides. But you still get to keep the advantages of the builder pattern as opposed to constructors, the easy to read code and not needing to define an exponential number of constructors. So how is it that we check this? Well, one way you can think of the correctness of using the builder pattern is as a typestate property. So if we have a builder object, you can imagine it being in different states depending on which of the required setter methods you've invoked. So we start in a start state right here, and then if you invoke both the name and the ID functions in either order, you end up in this accept state where you're allowed to call build. But if you try to invoke build early, that transitions to an error state because you have not invoked all the required property setting methods before you call build. So this is great. We've got a typestate automaton here. We have decades of work on typestate analysis. Why don't we just use an off-the-shelf typestate analysis system to try to solve this problem? Well, here, the problem, which I discussed before about whole program static analysis, is that this kind of analysis is expensive. And the root cause of the problem is that general typestate analyzers rely on doing a whole program alias analysis in order to soundly handle arbitrary typestate properties. So we wanted to avoid doing this kind of analysis for all the reasons that I outlined before. But we had an insight about how this typestate automaton looks. And the insight here is that the transitions only flow in one direction. So once you have a builder object that has reached the state where you can call build because you've invoked all the required methods, you never have a transition like this purple transition here, which takes you out of that state and therefore means you can't invoke build anymore. So once you get to the state where you can call build, you stay there. You never transition backwards. So this is a type of typestate property we call an accumulation property. And it turns out that if you're doing an accumulation analysis to check this kind of typestate property, you can do something much simpler. than what you have to do for checking arbitrary typestate systems. And these accumulation analyses are similar to some previous ideas in the literature, in particular work on heap monotonic typestates from Fondrick and Lino. So what are the advantages of accumulation analysis? Well, one key, probably the most important advantage, is that it's always safe and sound to under approximate. And in particular, you can completely under approximate your reasoning about aliasing. You don't need to do any alias analysis at all to build a sound accumulation analysis checker. And let's look at an example to see why this is true. So here we have a builder B, and we invoke name directly on B, but in order to invoke the required ID function, we do it through an alias B2. So now what's going to happen when we check this call to build at the end? Well, the worst case here actually is that we get a false positive. If you don't track the aliasing, your tool will think that ID was never invoked. But in the case of accumulation properties, that just means that you might think that a legal operation is in fact illegal, which leads to a false positive, but it does not lead to unsoundness. So this leads to this really nice way to design tools. You can build a basic sound tool with no alias analysis at all. And then as you apply it to code bases, you can add targeted reasoning about aliasing to bring down your false positive rate, but never compromising on the soundness of your tool. Another very nice thing about accumulation analyses is that we can implement them modularly, for example, as a pluggable type system. So let me show you how that looks for this case of builder patterns. So we need to write some annotations. So here, for the build routine, we write this called methods annotation. So what this says is that for whatever object you're passing as the this parameter to this function build, you need to have called the methods name and ID on this object already before you get here. One nice thing is that for the frameworks I mentioned before, like Lombok and AutoValue, that are generating this builder code for you, we've actually built integration so that we can automatically generate these specifications also. So we can figure out what methods are the required ones and then automatically reason in our tool about what called methods annotations should be present on these build methods. So in most cases, developers don't ever have to write this unless you're writing your own builders. And I want to note here that I've been talking a lot about object construction and builder patterns. So sorry, what this called methods annotation means is that these methods must have already been called, as I noted. But really, this can express any kind of pattern of the form always call A before B, which I think we've seen a lot in many scenarios. And so this checker is actually quite general, and we're continuing to explore what other interesting properties we can check with this technique. So now that you have these specifications about which methods need to be called before other ones, we need to verify the specifications. And we do this with a called methods verifier. One thing it does is a standard subtype checking at assignments. So we define a subtyping hierarchy where type is a subtype of another if it has more called methods. So in other words, that will ensure that when you invoke this method, whatever you're passing in as the receiver should be a subtype of called methods of name and ID, which means that you can have invoked more methods like nickname on that object, but you should definitely have name and ID there. So this is built into the checker framework. We didn't have to write any code here. So this ensures compatibility at all kinds of assignments. and also handles method overriding soundly. Within a procedure, we also do flow-sensitive inference of these called methods types for locals. It's basically tracking what methods are called on a particular expression. So as an example here, if we have a builder, initially it won't have any methods called. And when we see a call to name, we will update the type to have name in it. And similarly for ID, so that we can verify this call to build. So that's a high level of how this tool works. And I mentioned that we didn't have to do any alias analysis for soundness, but we did find one pattern, which I've already showed you, where we do actually need some alias reasoning for precision, or we get too many false positives. And that's this kind of use case where you're invoking these APIs one after another in a fluent manner. So if you just apply the technique I mentioned before, you're going to conclude that the only method invoked before build is ID, and you're going to reject this code. And the main reason is that the tool doesn't know that the object being passed in to ID as the receiver is the same object that's being returned, right? That we're threading the same builder object through these calls so that we can accumulate all these methods on that same object. So we needed targeted alias tracking for these kind of fluent APIs. And I'm not going to get into details, but we did this with a separate type-based approach. So let me just briefly cover some results here. One experiment we did was to study a class of security vulnerabilities, AMI sniping vulnerability, on an industrial code base. So we ran our checker on significant amount of code, over 9 million lines. We found 16 vulnerabilities with only 3 false warnings, and only 34 annotations had to be added in order to do this. So this was quite a good result in terms of overall effectiveness. We also looked at builder patterns based on these projects, Lombok and AutoValue. So here we looked at 5 projects with about 200,000 lines of code, and we were able to verify over 600 calls, and we found 1 true positive bug. Here we had to add some more annotations than before, 131. Sorry about that. I do think that many of these annotations could be inferred automatically, and that's some ongoing work that we're doing. And we had a few false positives. We got this great comment, though, from an engineer on one of these projects, and they actually fixed the bug that we reported. So that was pretty gratifying. So this tool is also available. It's actually now available as part of the checker framework. So I also encourage you to try this out. It's called the called methods checker. And like I said, this can really check any property of the form, always call A before B. So you don't just have to use it for builders. If you find a cool new use for it, please let us know. So in the remaining time that I have, I want to talk just a little bit about an ongoing project we have on applying these pluggable type techniques to doing resource leak detection. So what are resource leaks? Let me just explain it by an example. Here's some code that's adapted from the Apache Zookeeper project. And in this code, we're creating socket objects. And a key thing about sockets is that they have a corresponding underlying operating system resource. And in order to ensure that resource gets released, you need to call close on this object before it becomes unreachable. That's the only way to ensure that this resource is released in a timely manner. So the problem in this code is that this SO timeout function can throw a socket exception. And if that exception gets thrown, we're going to lose the last reference that we had to this socket, and the underlying resource is going to get leaked. And these kind of issues can turn into serious bugs because you can deplete system resources. So maybe even other programs running on the same operating system won't be able to open a socket or a database connection. And this can degrade performance. It can even turn into a denial of service attack. If someone knows how to send a request to your system that's going to leak a resource, they can just do it hundreds of times. And this is also really hard to test for, because if you leak one socket, maybe you don't notice. But if you leak 10,000 sockets, then you're definitely going to notice. But certainly writing unit tests for that kind of behavior is pretty difficult. So there are many existing approaches to try to prevent or detect these bugs. Java itself, in Java version 1.7, introduced a new try with resources construct. So you can write your code like this, and if you write it this way, the socket will automatically get cleaned up at the end of this block. So this is great when it applies, but it's limited for one reason, is that the resource has to be closed in this kind of static scope, right? So I can't take my socket and return it from a function very easily or store it in a field. We've seen a lot of code where you can't just immediately apply try with resources to fix the problem. Again, you could try to use typestate analysis. There's multiple papers in the literature that use typestate analysis to detect these kind of resource leaks. But again, we have the same problem as before. Now we're in the world of whole program alias analysis, and this can take many hours on larger benchmarks. So our observation is that if you squint your eyes the right way, leak detection is actually one of our accumulation properties. So here's an automaton for a simple maybe file or a socket where once you open it, you can write to it, and then you close the socket, and if you try to write to a closed socket, you get an error. So how can we express this issue that you need to close this socket before it goes out of scope? Well, you can just add going out of scope as a transition or an operation in this automaton. So now it's clear that before you exit or go out of scope, you need to call close. And this property of call close before you go out of scope is exactly similar to the called methods properties we were checking before. It's an accumulation property. So we've been working on a checker for this. And the property that we're trying to check here, we write it as must call, right? So you can write this annotation on a type, and it means that you have to call all these methods before any object of this type goes out of scope. And you can see this doesn't talk about resource leaks. Just like the called method system, this checker is going to be more general, and it can handle enforced calling of any method on any type. We have a checking algorithm that basically extends the called methods type system. We have to infer these must call types for expressions, and then we do a simple data flow analysis to track where expressions might become unreachable, so we can do this check that the right methods have been called. So again, we're an accumulation analysis, so that's really all you need to do to build a sound checker. But we found that you get many false positives, and we're still working on bringing this false positive rate down by doing some targeted aliasing reasoning. And one system that we've come up with is kind of a lightweight version of ownership tracking, which we've seen in a lot of academic work and also in real world programming languages like Rust. So here, we're creating a socket in this code example and returning it. And at the end of this method, S goes out of scope, but we don't want to report an error here because it's really the caller that's responsible for closing this socket. So you can think of this as a transfer of ownership from this S variable to the caller and wherever it stores the return value. So what we try to do is track an owning pointer. That's the pointer responsible for satisfying this must call obligation. And we perform ownership transfer at certain assignments and calls. But unlike other ownership type systems like in Rust, we don't need to invalidate a pointer after ownership has been transferred because we're only going after this must call property. We're not trying to prove something like, eliminating use after free errors, which does require invalidation. And so we want to reduce the annotation burden here. So we try to have some good defaults, but you can override them with your own annotations. So just briefly, preliminary results are that this analysis scales quite well. It's running in minutes on huge programs as opposed to hours. We have found a bunch of true positive bugs, we're still working on handling certain key coding patterns that we've observed, like storing resources into fields, and also wrapper types, things like buffered input stream, where you can either close the input stream that you've wrapped or the wrapper. We have some ideas on how to handle these cleanly, and this issue has come up in previous work like that of Torlak and Chandra on checking resource leaks with static analysis. So got a lot of ongoing work that I think would be also quite cool to do in the future. We're working on better type inference and introduction. We want to make these systems easier to adopt. So inference can help a lot there. And I think there's a lot of potential to even do things like automatic fixing of bugs, automatic introduction of suppressions to make these systems much easier to introduce. And we have a lot of ideas for more applications of accumulation. In particular, if you look at the specification mining literature, a lot of mined specifications involve these always call A before B kind of properties. So could we connect the specification miner with our checker and very quickly, check these properties or check which ones are likely to be real versus not? I think that could be quite cool. So in conclusion, I've argued that these pluggable type systems are increasingly viable in the real world, particularly because developers really want to prevent bad crashing bugs, and they'll write annotations to do it. And then I talked about NullAway for fast and practical null safety, and accumulation analyses for doing lightweight modular checking of type state properties. So thanks so much. I'm very happy at this point to answer any questions.